First of all, can everybody hear me? Still? Yes, okay, great, thank you. And well, welcome. Today, I will present you the thesis I've done called Interactive Cartography of Language and Memory in Patients with Focal and Pharmacoresistant Epilepsy, Multimodal Assessment. It was done in LPNC laboratory under supervision of Monica Baciu within REORG project. I would like to begin by thanking members of jury for accepting to evaluate my work and for their time. I will now present you quick guidance through today's talk. I will begin by providing arguments why we should study language and memory and interaction, and also why temporal lobe epilepsy should be used as a model for studying this interaction. I will present two main goals of this thesis work. I will then illustrate this problematic by presenting first two studies we did, in which we evaluated the protocol to study language and memory interaction in healthy participants, as well as temporal lobe epilepsy patients. I will provide final study in which we analyze functional connectivity of this interactive network during resting state and during recall. And we also analyze how it differs between temporal lobe epilepsy patients and healthy controls. I will conclude by summing up our main conclusions and interpretations. And I will also present some directions for future work. In all transitional slides, I will present chapter in which the work has been presented. And on the right, I will present studies in which the work has been published. So our main interest is language as a system in which we combine different codes to transfer our message. Specifically, we are interested in its cerebral representation. Language is a complex system and there are various sub-processes. However, in our work, we were interested in certain among them. For instance, articulatory phonological processing or speech production that is represented in the brain via dorsal stream, or here in this network of regions shown in green in precentral regions, among others. Then auditory phonological processing or speech perception represented by a network of regions in superior temporal region. Lexicosemantic processing supported by ventral stream or vast network of regions here presented in pink that spread through temporal, parietal, and inferior frontal regions. And syntactic processing that is supported by various regions, especially posterior medial temporal regions. As I mentioned in the beginning, or no, language is main function of language is to send our messages to others, to communicate them. So let's see how these processes are engaged in everyday communication. When we communicate with others, we formulate our message so that other person can understand us. We do so by relying on what we know about that person, what we think that person thinks or believes. In other words, we rely on common ground. Common ground is the shared knowledge between communicative partners. Now, as I explained this, you saw how processes I've previously described, language processes, cannot reply to all demands within this communicative context. That is why our communicative behavior relies on cognitive interaction, specifically interaction between language and memory. Now, of course, this communicative behavior, within it, language is supported by multiple memory systems. However, we are specifically interested in long-term declarative memory that refers to maintaining knowledge and then being able for a long period of time and then being able to recall it consciously. It can be separated in semantic and episodic memory, semantic focusing on concept knowledge and episodic focusing on our proper experiences. And now, how is it connected with language? Well, we can see that already there is a domain that is common between the two, semantics. And as I mentioned also, we are interested in how it is represented on cerebral level. So let's see memory network. And here I present math model of memory network. In that model, it was proposed that semantic processing is supported by anterior temporal system, whereas episodic recollection is supported by posterior medial system. These two systems are connected and integrated via hippocampus, who performs relational binding between the contents of these two systems. Coming back to language system, we see that semantic network in memory and in language are partially overlapping within temporal regions. However, now we can ask, is the only contribution and interaction between declarative memory and language happening through semantics? Or are there some episodic contributions? So are there any evidence of language and episodic memory interaction? Yes, there are. And we have evidence from different research fields. For instance, research and witness reports show us that language can influence memory retrieval. Research in developmental psychology and bilinguals show us that language becomes part of an episode. And also language and episodic memory share some white matter paths, such as imperial frontal orbital fasciculus. If you remember, I said that hippocampus is the region that connects two memory systems. Now, researching patients who have damage of this region showed that they have problems with memory. But what is interesting is that they also have problems with language. These results, together with the concept of common ground, led to the proposal that there exists language and memory interface specifically supported by hippocampus, and that hippocampus allows access and integration of the information that language uses in communicative context. However, there is another type of a neurological disorder that can serve as a model for studying this interaction between language and memory. That is temporal lobe epilepsy. Why? Well, to begin with, because epileptogenic network that is engaged in seizure propagation in these patients is focused on temporal lobe. Also, it is usually followed by hippocampal atrophy, that is different patterns of hippocampal cell loss. These patients are often resistant to drugs, which means that in them, we can study cortical reorganization that happens as a consequence of either epilepsy or after surgery. Importantly, these patients show deficits both in language and in memory, and they're even in further risk of cognitive decline after surgery, which is why in these patients, before surgery, a detailed preoperative mapping of language and memory is done. Now, based on what I've just said, what we propose is that this mapping should be done in interaction. So not studying each of these functions separately, but their interaction. So to sum up, the arguments I presented were that language and memory interact to support our everyday communicative behavior. They share some regions and also neural paths. And we saw that damage of hippocampus and regions within memory network can reflect in language difficulties. Within this framework, we propose two main objectives of this thesis. First one that is more fundamental, and that is to map language and memory interactive network in healthy participants to understand how communications between this function is happening. And second one is to investigate the reorganization of this language and memory network in temporal lobe epilepsy patients. The idea was that findings related to this goal could provide us some practical implications for clinical practice. Within this framework and within REOC project, there were several studies that have been performed. However, today I will focus on these three in particular. In the first and second study, we mapped interactive language and memory network using a protocol developed within this project. Study one focused on healthy participants, study two on temporal lobe epilepsy patients. And in the final study, we analyzed functional connectivity of this network and how it changes from intrinsic to extrinsic state, and what are the differences in this change between healthy participants and temporal lobe epilepsy patients. All 3 studies have been published or are accepted for publishing. I will now present the first 2 studies. In first study, we had 90 healthy participants that performed our Jet2Rec protocol that I will, after this, explain. And in study 2, we had 18 left temporal lobe epilepsy patients. Now, our patients were statistically older, significantly older than our healthy participants, which is why within all analyses where we compared those 2 groups, we controlled for age. Finally, to see if the networks we managed to find in these 2 groups using this protocol really corresponds to language and memory networks, we also performed meta-analysis using NeuroSynth platform, in which we searched for keywords, language, and memory, which provided us with around 1,000 and around 3,000 studies. Based on these maps, we created meta-analytical expected language and memory network. I will now present the protocol developed within reorg team. This protocol, Jet2Rec, is called Jet2Rec because it consists of sentence generation and 2 recollection runs, which is recognition and recall. I will now explain each of these. Before entering the machine, participants were only explained the first task. They did not know how other 2 tasks will look like. The first task, sentence generation, had block-based design. There was a generation condition in which participants heard words. Every time they heard a word, they should generate sentence in their head. They also had a control condition during which they heard pseudo word. When they heard pseudo word, they were asked not to say anything. Second task, recognition, had event-related design. In this task, participants saw now images and they were asked to respond by pressing key response, whether objects shown in images were presented as words during the first task. So did they hear the words that were presented in the images? We had old images. Those were images of words that they did in fact hear. And they had new images. Those were the words that they didn't hear. There was also control images to control for motor activations. Now, in this task, what is important is that we had a change of modality, meaning instead of hearing words, they saw pictures. This was done in order to enhance episodic memory and hippocampal activation. Finally, the third recall task had again a block-based design, and participants heard again the words they heard in the first task. Only now they were asked to recall and repeat the same sentences they performed in the first task. To recapitulate, Jet2Rec protocol consisted of 3 tasks that were all specifically designed to engage both language and memory interactively. In the first sentence generation task, participants, in addition to performing sentence generation, also performed implicit encoding. In the second recognition task, in addition to recognition, they also performed implicit image naming. And in the third recall task, in addition to recalling, they again produced sentences. Here are the results obtained in healthy participants. Now, before I present them, I will just note that here, for illustration purposes, we present activation maps obtained on a lower threshold. However, results were performed on on higher threshold with correction for multiple comparisons. So during the first task, sentence generation, participants indeed activated regions that are supposed to be activated during articulation, during speech production, such as inferior frontal gyrus, supplementary motor area. They also activated lexicosemantic network in temporal regions. When we focused on implicit encoding, so only those words that they actually correctly recognized in the second task, we also found hippocampal activations and anterior hippocampal activations bilateral. During recognition task, we found regions that are part of recollection network in parietal regions, also parahippocampal and posterior hippocampal regions. And we also found regions activated during image naming, such as inferior frontal region and SMA. Finally, and fusiform gyrus. Finally, in the recall task, we had a network that resembled all networks combined. So the vastest network that contained frontal, parietal, temporal regions connected with language and memory. And we also found right hippocampal activations. In left temporal lobe epilepsy patients, we found activations that resembled those found in healthy participants. So for sentence generation task, we found activation of inferior frontal gyrus, temporal lobes, and also left hippocampus. During recognition, we found activation of memory regions such as posterior parietal regions, as well as left hippocampus. And again, in this recall task, we found a vast language and memory network that included regions for speech production, lexicosemantic processes, but also memory recollection. And we also found activation in left hippocampus. Then we compared healthy participants with left temporal lobe epilepsy patients. And maps that I present here, the regions in yellow represent actually regions where patients had reduced activation, so lower activation than healthy participants. We didn't manage to find one specific reorganization pattern as we expected, but what we found was that actually these regions were engaged in control and attention. So we found regions that have integrative capacity, such as fusiform gyrus. We found parts of attentional networks, such as regions in parietal, or regions that integrate, such as inferior frontal gyrus. We then also analyzed the lateralization of found activations in healthy participants and temporal lobe epilepsy patients. What we found was that actually patients had more variable activations, specifically in hippocampus during sentence production and in frontal lobes during recognition and recall, which could explain why we didn't find one specific reorganization pattern in our patients. Then we compared the networks we obtained in our participants, in healthy participants, and in temporal lobe epilepsy patients with meta-analytic network that was based on almost 4,000 studies. And we actually found that networks resembled, meaning that we indeed managed to activate what was expected as a language and memory network. Nevertheless, there were some differences. For instance, using our protocol, we didn't manage to find as wide activations in parietal regions as expected by meta-analysis. And also, even though we found activations in hippocampus, we didn't have as wide coverage as did meta-analysis. Nevertheless, using our protocol, we managed to activate the cerebellum more than it was in meta-analysis, as well as putamen and thalamus. These regions are known to be engaged in language and memory, and they're often neglected and left out language models. To sum up results of first study, we saw that using this protocol, we can indeed activate interactive language and memory network as expected via meta-analysis. That is, using this protocol, we found a vast frontotemporal parietal network, also containing subcortical structures. This is a dynamic network in sense that it changes from task to task. We didn't find one specific reorganization pattern in our patients. However, the regions that they showed reduced activation of were the regions that were previously found to be engaged in integration and cognitive control. Nevertheless, these studies left us with some open questions. First of all, we're talking about network. So how are the regions of this network communicating between themselves? We say that it's a dynamic network, but how does it really adapt to task demands? And finally, does this differ between healthy participants and temporal lobe epilepsy patients? To answer these questions, we performed our final study. In this study, we also included resting state in order to to evaluate intrinsic state. During this resting state, participants don't perform any kind of task. They just observe a cross on screen. And as an extrinsic state or task, we use recall task from our direct protocol, the last task, because it mapped the majority of network. By comparing in each group resting state with the recall task, we observed what we call state reconfiguration. So how network reconfigures when starting a task. We compared healthy participants and temporal lobe patients in terms of each configuration to see what is the reorganization of configuration, meaning how it differs in temporal lobe epilepsy patients in comparison to healthy participants. And we also observed how this state reconfiguration, so change from intrinsic to extrinsic state, how it differs from healthy participants, temporal lobe epilepsy patients, and we term this reorganization of state reconfiguration. So we observed, we analyzed state reconfiguration in order to see, what network is trying to support with its adaptation, what kind of processes in response to the task. And we compared healthy participants and temporal lobe epilepsy patients to see what are the additional sub-processes that network is trying to support when one of the interface is imperiled, such as it is in temporal lobe patients. In this study, we had 90 controls and 16 temporal lobe epilepsy patients. Now, they were both left and right temporal lobe epilepsy patients, but we controlled that they all had left lateralized language network. They performed resting state as well as direct protocol from which we used recall task. For our network, we used previously defined language and memory network within our research team, and we translated these regions into resting state networks. For each of this region, we extracted signal variation, so time series, and then we correlated regions simply to obtain one correlation matrix. We obtained correlation matrix for each group, for each task. On each of these correlation matrices, we then performed community analysis. Now, this analysis comes from graph theory, and the idea is to see how network segregates, meaning how network segregates in these modules or group that are composed of regions that have higher connection between themselves. This segregation tells us what are the specialized processes. Segregation of network is one of its properties. The other one is integration. So network also communicates between these modules. So for each region, we can see how it communicates with regions within its module called intramodular connectivity, and how it communicates with regions in other modules called intermodular connectivity. By crossing these two values for each region, we can define their roles. There are a couple of roles here we used 4, but our main role that we were interested in was connector hub, because those are the regions who provide integration within network. They communicate with other modules, but they're also central in their own module. And here are the results. So these alluvial diagrams show on one side configuration of modules during resting state, and on the other configuration during extrinsic state or recall task. These rivers show how regions change their modularity participation, and these values show how much modules changed from resting state to recall. When we analyzed this reconfiguration in the healthy participants, we found several interesting phenomena. First of all, when moving to task, this was the most interesting, there is a segregation of temporomesial module that is composed precisely of hippocampus and amygdala. And this corresponds well with the proposition of language memory interface and also of MAT model. Also, during resting state, there was a module that was composed of language regions And when participants move to task, these regions actually spread through to various different modules. The most flexible were temporal limbic module, in addition to this one that is dispersed. And so we see that changes happens on the level of temporal regions. And then we analyzed temporal lobe epilepsy patients. In healthy participants, we saw that segregation remained the same, meaning they had the same number of modules during resting state and during recall. However, in temporal lobe epilepsy patients, we see that first, during resting state, they had lower number of modules, so lower segregation, but when they move to task, they have higher segregation. Importantly, we didn't find segregation of this temporomesial module. Instead, we found segregation of two other modules, temporocingulate and temporoparietal. This temporoparietal was composed of exclusively attention and control network regions. Also, temporal lobe regions had lower flexibility, meaning they didn't change the module. So to sum up these results, we see that reconfiguration in healthy participants is based on movement of key language and memory regions. Whereas in temporal lobe epilepsy patients, these regions have reduced flexibility. They don't change as much. We were then interested in integration within network. And so here I present a graphic where on epsilon, we have mean number of connector hubs for each of resting state networks. So of each of these large networks. What we see was that in healthy participants, as they move from resting state to task, they have lower number of attentional regions that act as a connector hub of connecting network. Whereas patients, on the contrary, have increased number of these network regions that act as connector hubs. Also, healthy participants have reduction in control regions, where in patients we don't see this. We then wanted to see what is happening on the level of intramodular connectivity, meaning how modules connect with one another within a network. And we saw that this capacity was disrupted in temporal lobe epilepsy patients, both during rest and during recall task. We then analyzed this capacity, this intermodular connectivity for each region. What we found was that during resting state, it was hippocampus that had increased intermodular connectivity. Well, this phenomenon has already been found in the literature, and it was named hippocampal paradox. And it was proposed that this is a consequence of seizure propagation and that it's not functional. And within our study, we managed to confirm that, because indeed, in our task, not only that it didn't have higher intermodular, it actually has lower. So their ability to connect network was lower in temporal lobe epilepsy patients. To conclude, we found that in healthy participants, language and memory network reorganizes by the movement of key language and memory regions, especially segregation of this temporomesial module that could be acting as an interface between language and memory. In temporal lobe epilepsy patients, the configuration mechanism is a bit different. There is a higher segregation of modules, and there could be several explications for that. It could be because there is a compensatory mechanisms of specializing certain functions to support network integration. Also, it could be that it is due to the loss of distal connections. And finally, having more modules could actually be a mechanism to stop seizure propagation. And now I will summarize our conclusions and present perspectives. As I mentioned, our first goal was to see how language and memory interact within their interactive language and memory network. We used a specific protocol to engage this interaction, and we found that we can first indeed map it with our protocol, and that it is a vast frontotemporal parietal network that also includes subcortical structures. It is a dynamic network that indeed reconfigures depending on our environmental demands. And based on our results, we propose model of language and memory dynamic interaction, where we say that we believe that the interaction is happening on the level of episodic buffers. Now, this module, there are of course different models of language memory interaction, such as Ullmann's model or Hargut's model. However, in those models, they either focus on a specific language process or they don't include the whole declarative system. So in our model, we used the results from our network analysis and we situated them within other models of language and memory and other theories. We wanted to explain, to model what is happening when a person is trying to retell what they said before to somebody else. So as we saw in the study, we first have movement reconfiguration from intrinsic to extrinsic state of this network. We believe that when a person hears a topic, there is word recognition and lexicosemantic search that is performed by this frontotemporal parietal module here presented in purple that contains majority of ventral pathway regions. The rest of the semantic network is distributed here in temporal limbic module that actually supports concept information. And we believe that this module actually provides a retrieval queue for retrieval of the specific episode. At the same time, this frontoparietal module, especially its parietal parts, provide context for the episode. And it is this temporomesial hippocampal module that provides the integration of the content and provides the integration crux. However, again, this frontotemporal module provides the details of the episode, and with these details, it becomes relived, meaning we're becoming aware of that, and it transfers into semantic representation. Then semantic representations through the implication of frontal module are transformed into speech. During all this time, we also believe that there is a parallel binding and encoding of the episode that is just happening, and it is supported by temporomesial module. So our proposition is that language memory interactions happen in the level of these episodic buffers because it was recently proposed that precisely these regions perform two episodic buffers. In perspectives, well, this is a hypothetical model. So we have to evaluate it further using different methods, different techniques, but also using different samples. Our other goal was to investigate how this interactive network is reorganized in temporal lobe epilepsy patients with the idea of having practical clinical implications. We saw that yes, temporal lobe epilepsy patients indeed activate language and memory network similar to meta-analysis and to healthy participants, but their mesial regions have reduced integrative capacity, which is why they use control networks and attentional networks as compensatory mechanisms. The question is, how informative is this for clinical practice? And can we eventually predict cognitive outcome after a surgery using this data and this approach? First of all, we are now using our approach on an individual level because in clinics, it is individual level that is of importance. We are mapping language and memory network in each patient before surgery, and then combining these results with neuropsychological scores and clinical data, we try to understand how network reorganizes after surgery. We are currently trying to see what is the added value of these preoperative language and memory networks for surgery planning, but also the reorganization of networks combined with neuropsychological scores could be informative for prehabilitation and rehabilitation. And finally, the main question is, well, are we now able, using these data, to predict what will happen on cognitive level with patients after surgery? And because this is a complex phenomenon that includes multiple factors, we use multimodal approach, meaning that we combine fMRI results with anatomical results, neuropsychological data and clinical data. Our preliminary results show that using all of these group of variables together, we managed to group better patients who have cognitive decline after surgery and patients who don't show change after surgery, much better than we managed when we used each of these group of variables separately. And I would like to conclude by thanking the reorg team that has been working on this project with me together, and I hope we'll continue to work on it. Thank you very much.